So in today's lesson for our Danfoss AK PC pack controller training, we'll be covering our multi-ejector. We'll do a little background on the ejector first for anyone that's not familiar with it, and then we'll transition into how programming in the pack controller supports the ejector itself. For anyone not familiar with the ejector technology, this is the ejector is not something that's specific to CO₂ or refrigeration even. It's just a technology that's being used in this refrigeration application. So in general, the purpose of the ejector is to use high pressure flow. In our case, with the CO₂ rack design, it would be the flow out of the gas cooler, and use that flow to bring in flow from another area, and a lower pressure area specifically, which in our case would be the suction of the medium temp compressors for a design that's utilizing these ejectors. So that's where you'll see these utilized, is taking advantage of the high pressure flow out of the gas cooler and bringing in that suction flow inside of a mixing area inside of each ejector cartridge, and then coming out at a medium pressure between the low pressure of the suction, the high pressure of the gas cooler. And as you'll see in some of the schematics here in the next few slides, this is then taking those the CO₂ mixed from those two areas into the receiver, and that allows us to bypass the compressors and reduce the amount of work that needs to be done on that fluid. There are different types of ejector, and so you can see the three categories that we have here defined. Each of these is a different design, a different ejector. So the cartridges inside of the block itself, each is intended for its own application. We have a high pressure ejector that's just focused primarily on vapor or gas. We have a low pressure ejector that's also focused on just gas, and then a liquid ejector that can also do liquid. There's some differences here in each one of these in what we call a lift or entrainment ratio, which is essentially the ability of that gas cooler pressure to lift up flow from the suction side. And so that differentiates some of these options as well. Capacity, when you look at the first two, which are both vapor, and may ask, well, when would I use a high pressure versus a low pressure? The capacities of these two can be different. The high pressure typically has larger capacities it can support than the low pressure. And so each one may fit into its own design scheme, per se. And then there's also environment or the temperature considerations taken here. So high pressure, low pressure vapor ejectors, these may be a little more tailored towards stores and locations where it's generally warmer for larger parts of the year, whereas the liquid ejector may be a better fit for some of your colder climates to be able to take the energy savings out of it for a longer period of time. So we'll get into all this a little bit more here as we move forward, but just keep in mind that there are three different models, and for our programming exercise in the system manager, or in the pack controller rather, we'll be focusing primarily on the high pressure ejector, just based off of current usage. So if we now go back to our schematic of a CO₂ booster rack, and we look at where does the ejector fit in. So you can see here at the top left corner, coming out of the gas cooler, the ejector is being shown located here. That is where you would see it installed on the system. So not up on the roof, it would still be at the rack, but it would be piped into the outlet of the gas cooler. It is intended to replace the high pressure valve. So all of the logic that we've covered in our earlier sessions on the high pressure valve, the ejector is using that same decision making and logic to decide how to control the ejector as well. So if you recall back on that lesson, we were looking at our gas cooler outlet temperature, and that dictates the pressure target we want to control to out of the gas cooler. And so this ejector is staging solenoids and cartridges inside of a block to allow that pressure to be maintained at the level we want it to. And so there's no extra logic from that standpoint as far as additional pressure transducers, temp sensors that we need to install along with this. It's using our existing data and our existing sensor values to decide when to use this ejector and how much. So again, the inlet line of the ejector is coming from the gas cooler. You can see the blue line here in the middle connection of the ejector. This is going to our medium temp suction. As we said, the whole premise here, and we don't have arrows, but the flow of the medium temp suction would be going in this direction into the ejector. When pressures are high enough coming out of the gas cooler, that's where we're able to kind of siphon in refrigerant on the CO₂ line from the suction coming in here. And by doing that, however much flow we are able to bring in based on how high the pressure is at the gas cooler, that's all refrigerant we're able to take off of the medium temp compressors and reduce some of the energy consumption and compressor usage in general there. So those two lines make up kind of your inlet flow into the ejector, and then our bottom green line is your flow out to the receiver. So here's some pressures that we have. These are your standard pressures. Nothing changes here with the ejector. The one thing that you'll want to keep in mind here is that when we look at this design, we do have the parallel compressors in place. And with a high pressure ejector, we will always see the parallel compressors being used along with them. And the reason there is if we don't have the parallel compressors and you just kind of follow your path of the medium temp suction that's being pulled in, if we take the medium temp suction, and here you can see 25% of what's on the medium temp suction, we're bringing back into the ejector and bypassing that around the compressors. So if we take that 25% back into the ejector and that mixes in back down at the receiver, if we didn't have the parallel compressors, and that 25% would just end up right back on the medium temp suction line anyway as it passes through the receiver bypass valve. So we really wouldn't accomplish anything by doing that. So that explains the reason we need the parallel compressors, because when we take that 25% back up to the ejector and have it then flow down into our receiver, now that 25% can be pushed up to the parallel compressors, where what we covered in our last session, we know we have a smaller compression ratio here because the suction pressure that the parallel compressors is working with is much higher than the medium temp compressors. And so now that refrigerant that we've pulled off of the medium temp suction is being compressed at a smaller compression ratio, which is using less energy. So we will always see the ejector, a high pressure vapor ejector, being utilized along with parallel compressors. It's a side view of what the ejector looks like. So we use a staged approach. This is not a modulating device in any way in terms of driving to opening degrees. We use a series of solenoid valves, and inside of each solenoid valve is a cartridge, or attached to each solenoid valve is a cartridge inside of the block, we call it, of the ejector. We do have different capacities, so you could see 4 cartridges and 4 solenoids. You could see 6, like you see here. But these cartridges are where the refrigerant is mixed and then pushed out to the receiver. And so we'll stage these cartridges depending on how close to that pressure target out of the gas cooler we are. So if we're well above our gas cooler target, then you can expect to see more solenoids energized and more cartridges being used. And then as our gas cooler pressure is dropping down below our pressure target, you can expect to see some of these cartridges and solenoids being staged off and not used. I'll also just point out quickly here at the beginning of the connections, you see this, we do have a strainer as part of the block. So for anyone that might be working directly on the ejector itself, servicing it potentially, it's good to know that this strainer exists right there at the inlet of the block. We're just showing an example here where as pressure's working through the ejector, we've staged on 3 of the 6 cartridges here. Cartridges do have a mix of capacities, so you may see different combinations staging on depending on exactly how much capacity we need out of the ejector as a whole. So we're back to our larger schematic now, showing the full rack. So here what we're trying to highlight is that when we're in colder ambient conditions, so we still have our ejector here coming out of the gas cooler, as we've talked about. We do also have, in this example, a high pressure valve in parallel with it. This is fairly common to see in rack designs that are using the ejector today. The high pressure valve can be a bit of an emergency backup to the ejector in case anything were to ever happen to the ejector itself. So it's not uncommon to see both the ejector and the high pressure valve being used, but in those situations, the ejector will always have the lead or the primary control function out of the gas cooler to maintain pressure there, and then the high pressure valve is only there as a backup or an emergency is needed. So in this example, we're showing that we have lower conditions, colder conditions. So 60 degrees, only about 750 PSI on our condensing pressure discharging out of the compressors here, both medium temp and parallel. When we're at lower conditions like this, 750 PSI, when we mentioned the lift of the ejectors or the ability to bring in medium temp suction and needing a good amount of pressure coming into it from the gas cooler to do that. When we're in these colder conditions like 750 PSI, you're not going to have enough pressure coming into the ejector from the gas cooler to bring in anything from the medium temp suction. And so really nothing coming in here. The ejector is essentially just acting like the high pressure valve would otherwise. We're just modulating pressure out of the gas cooler, and you're not getting really any energy benefit of the ejector in these colder conditions, since it's just processing the gas cooler mass flow and dumping that directly into the receiver like the high pressure valve would. When we're in warmer conditions, like you see now here, so now we do have a higher pressure coming out of the gas cooler. So now we're saying 1300 PSI. So now as that flow comes in, that is enough flow to bring in something from the suction side. Here you can see 22% showing coming into the ejector from the suction accumulator. So this is 22% of our mass flow. That 22% is able to be brought in because of the 1300 PSI out of the gas cooler. Those two fluids that fluid at those two conditions mix inside of the ejector cartridges, come out into the receiver, and then that vapor that's part of that mixture is then, now that we're in our warmer conditions and have a higher load, now we're expecting that vapor to be pushed through the heat exchanger that we talked about in our last session and be pushed over to the parallel compressors where we have that higher compression ratio and can save some energy. So this is an example of how that refrigerant would flow for the high pressure ejectors and bringing in extra mass flow to go over to the parallel compressors on top of what would happen if we didn't have the ejector. Without the ejector and just the parallel compressors, like we had talked about in our last session, we would just be looking at any vapor off of the gas cooler to be passed over there, but not considering or able to bring in some of that mass flow off of the suction line. So when we have the design, like we showed on the previous slide, where the high pressure valve is there as a backup to the ejector, it works very similar to the flash gas bypass valve on the receiver with the parallel compressor as well, as far as this being not just sitting there as a spare or a backup, but actively looking to see if it needs to supplement what the ejector is doing. And so what you see here is two graphs that are part of the same scenario. Our red graph is our gas cooler outlet pressure. You can see here we start in a middle range around our set point, our horizontal line being our set point. We're starting just below that, and then that pressure continues to increase. Down here, the yellow line is the capacity of the ejector, and the blue line is the capacity of the high pressure valve. And so what this example is describing is a situation where the ejector has gone to a full capacity, 100% capacity, but the pressure continues to climb at the gas cooler. And internally in the pack controller, what it will do is identify that situation and say, ejector is maxed out, it can't do anymore. I'll now go ahead and add the high pressure valve into this and begin to open that up slightly. And then the more and more is needed, to supplement the ejector. And so this could be by design, this could be an emergency situation. Sometimes ejectors could be slightly undersized to be able to take more advantage of them in colder conditions. And then in those 1 or 2% times of the year where you're at extreme highs for ambient temperatures, maybe the ejector is slightly undersized and needs the high pressure valve to supplement it in that way. Otherwise, it could be an indication of a strainer problem, something blocking the strainer. Solenoid coils have failed, something specific to the ejector that needs to be looked at. And so moving that over, this is another graph that just kind of supports what we've been saying. So the graph on the left is just showing a system that has just parallel compression, no ejector. And as our ambient temperature increases here, you can see the ambient temperature on the x-axis of this first graph. Our blue line is our medium temp suction capacity, and our red line is our parallel suction capacity. So without the ejector here, you can see as the temperatures get warmer outside, the medium temp is used more and more linearly, and then exponentially more the parallel compressor is also being used. So it's great that the parallel is being taken advantage of more here, but we're also not seeing a decrease in our medium temp capacity. So energy usage overall would continue to climb here. When we add the ejector in, though, when we look at the graph on the right, we can see that as that same ambient temperature increase occurs, because the pressure is also increasing at the gas cooler as this temperature is going up, now we have more pressure that's able to siphon in refrigerant flow from the medium temp suction. And because as the temperatures increase and pressures increase at the gas cooler as it gets warmer, we're able to bring in more and more into the ejector from the medium temp suction, which means we're able to utilize the medium temp compressors less and less as that happens. So that's why on this graph you see the blue line again here, the medium temp suction capacity, that kind of tops out here in your 70s, between 70 and 80 degree range. And then it actually starts to decrease again while your parallel compressor usage increases more and more with the ambient temperatures increasing. So this is a good thing relative to the first graph because we know using the parallel compressors takes less energy than the medium temp compressors. So this is exactly what we want to take advantage of with the ejectors, is being able to use those more energy efficient compressors, the parallel compressors, and use the medium temps as least as possible. And so this graph just gives you a quick idea of some of those percentages that you can expect from an energy saving standpoint on an average system ballpark here based on your gas cooler outlet temps. So our baseline here up along the top would just be a standard booster system with no parallel compression and no ejector. And you can see as you start to add in the parallel compressors, which is the light blue line and dark blue line here, you're starting to get into high single digit or maybe even double digit energy savings as you get across your critical point. As we're getting into our 85 to 100 degree temperature at the gas cooler outlet, you can start to see double digit energy savings just by adding parallel compressors alone. And then when you start to add in some of the different ejector options we have, so the olive green line being the high pressure vapor ejector we've been discussing, you can see that you push towards almost 20% energy savings in theoretical calculations. And then the combination ejector that we're not going to go into a ton of detail today on, but that we did mention initially, you can see that that can offer up as much as 20 to 25% energy savings on an average system. Just one last slide on sort of the ejector itself and the startup of it. So when a system with the ejector is being started up, we don't typically like to start it up with the ejector on right away. We like to disable it and allow the high pressure valve to be the initial control point. It lets the dirt, the debris in the system, we make sure we get that back into our filter dryers and the other areas of the system that are meant to collect that. And then after a little bit of runtime, maybe a few days, then we can go and add the ejector into the control strategy that's being used. And it's a pretty easy switch that we'll show you in service tool. So when we're doing that process, that strainer that we looked at on the side view of the ejector early on, it's just 4 bolts that hold it in. So it's good after the startup, right before you're about to add the ejector into it, just double check that strainer just to make sure there's nothing there blocking flow into the ejector. It's an O-ring that can be replaced anytime you need to pull the filter or strainer cartridge out, and the O-rings can be reused. So you can just kind of keep 2 on hand and swap between the 2 of them for any time that you need to check that strainer for any possible blockages. We'll go ahead and bring the service tool in now. Good news here with the setup is that it's very minimal, what we need to change to support the ejector control. Again, there's no extra pressure transducers or temperature sensors. And we're using all the initial data out of the gas cooler to really drive what we're doing with the ejector. The ejector is considered part of the high pressure control since it's serving the same purpose as the high pressure valve. So we would just be going right into the high pressure control section, service tool. And then here, our first page is still linked to the high pressure valve itself. So when we go over to the second page now, that's where we would be configuring our ejector. Nice thing here is we don't have to set up a bunch of individual settings. The main goal here is just to select the model type we have, and this is a label that will be on the side of the ejector if we're not sure of exactly which one we have. But you can go in here once you know what the model type is, just make that selection, and then it'll show you how many ejector blocks it has, and then you just get a few setup options down below this. Adaptive liquid control would actually be something associated with the liquid ejector, so we won't even need to worry about looking at those settings for the high pressure vapor ejector. And so you're really just looking at your KP and your TN here to see if you need to speed up or slow down the reaction time of the ejector and how quickly it'll react to pressure changes out of the gas cooler. So once we've done this, this is it for the initial setup, and then it's really just a matter for configuration of assigning your relays. And so we would get down in here, and then if we had the 5 ejector blocks that we're utilizing, then we would just go ahead in and put the relay assignments in. Now, one thing I'll do, I was starting there just to put another relay board in our configuration, but actually one thing that you want to keep in mind here, and this is documented in our literature as well, but the ejector cartridges, they kind of go in order from smallest to largest capacity. And the smallest cartridges, the smallest capacities, they're going to stage very frequently, a lot. So we always want to make sure, especially the first 3 or 4 ejectors, if possible, that we get them on solid state relays. And so if you recall from some of our earlier sessions, on the pack controller, you have 4 solid state relays. We do have one already dedicated to our oil valve, the solenoid between the separator and the reservoir. So here I'm going to add 3 of the ejector cartridges to our other solid state relays that we have. So on the pack controller itself, relays 13, 14, and 15, which are your second, third, and fourth relays, are solid state relays as well. So we can put those first 3 cartridges on there, expecting them to pulse again at a very high frequency. And then maybe the 4th and 5th ejectors won't be pulsing quite as much. So we can put these, I think we had back up in our last session, we had an extra relay board we put in for the 2 parallel compressors. We only used 2 relays on that board, 9 and 10. Maybe we can use 11 and 12 here for our other 2 ejector cartridges. And now back on our overview screen now, you'll see that you have this icon here for the ejector, where we can go in and see some statuses. I just want to go into this section quickly because now you can see here when I talk about turning the ejector on after a few days of runtime, where do you actually do that? It's right here in this screen under control mode. So for control mode, this will start in an off state so that the ejector is not considered part of the logic or something that can be controlled. It will leave all the solenoids off. And your high pressure valve will be what's used to maintain gas cooler pressure. After those few days, when you're ready to turn this on or have the ejector in, and you can just change this into an auto mode. If you ever needed to put the ejector to a forced capacity, you can always do that with this manual option. But typically you're just going in here to put this to an auto mode. And then if you need to service this a week later or a year later, you can always come back in here, change the ejector to off. The pack controller will automatically put control back to the high pressure valve. And then you can isolate and do whatever you need to from a service standpoint for your ejector. Otherwise, that's it. It's again a relatively simple add in from a programming standpoint, where you're just choosing your model type and then coming into the status screen here to set the control mode to auto. Okay, so thanks again for joining our lesson today. Hopefully this helps with a better understanding of how our high pressure vapor ejector works.